Let's just go really briefly into something called the electromagnetic spectrum today. And a good place to start when talking about these electromagnetic waves is an electromagnetic wave we already know, light. It's part of the electromagnetic spectrum. It is an electromagnetic wave. And by identifying some of the facts that we know already about light, we can then just positively transfer all those facts and start using them to talk about the electromagnetic spectrum as well, and just start to have conversations about the EM spectrum right away based on knowledge we already have. So let's just quickly have a pause, have a think, jot down some ideas. How does light travel? How does the electromagnetic wave, because we can now say that, the electromagnetic wave of light, how does that travel? Pause and come back to me. So we know light travels as a wave. We can now say light travels as an electromagnetic wave. If we want to add in a little bit more detail, we know these are transverse waves. We know that. We know that light travels in straight lines from when we have drawn ourselves, ray diagrams and stuff like that. And we also know that light can travel through a vacuum. It doesn't need a medium to travel through. And we've observed that from the fact that, light comes from the sun. The electromagnetic wave of light comes as a transverse wave in straight lines, in rays of light, and it can travel through the vacuum of space from the sun to our planet Earth and eventually to our eyes. So these are facts that we already know, not new information, but we can then start using it, and then start using these facts to talk about the other EM waves. So what the hell do I mean by an EM wave? Well, I mean something that's transverse. I mean something that can travel through the vacuum of space, something that can travel at the speed of light, about 300 million meters per second. Yeah, that's C value, which we've met in, energy equals mass times the speed of light squared. That C value isn't really just the speed of light, it's the speed of electromagnetic waves. So again, this is more information we can positively transfer forward and just start using when we're talking about these other waves. And then here's kind of a diagram in the X and the Y axis showing what's going on, showing us that we have it, going up and down from peak to peak or to any similar points. We have this lambda, the wavelength, and there's a couple of other things going on. There's a magnetic field of moving out in this X-axis, and there's also the bit we were looking at there, the Y is actually the electric field, and that's where these two ideas of electro and magnetic are coming from. Two concepts we're not going to focus on right now. We're just going to focus on positively transferring this information we already know and worry about that electric field and that magnetic field a little bit later. But if you want to go research that and resolve that in your own time or watch some of the other videos, go for it. I can only encourage curiosity. Here is the electromagnetic spectrum. The electromagnetic spectrum being this range of 7 waves, which we've got all named here, moving from a wavelength which is really long to a wavelength that is really short. Okay, so the radio waves are the first members of our electromagnetic spectrum, and they're really, really long. So they're 10 to the power 3, right? So, about 1,000 meters tall. Size of buildings. Pretty tall, right? Now, next thing we have is if you take a radio wave, which we had here, and you reduce its wavelength, so if you squash it a little bit, it transforms. The transverse wave transforms, and it becomes a microwave about the size of humans. You take that microwave and you squash its wavelength a little bit more, it becomes infrared, IR. Squash it a little bit more, it becomes the visible light, which we all know, and that whole spectrum of colours that comes within there. The Roy G. Biv of colours along the bottom. Take that visible light, you squash a little bit more, we become ultraviolet. Ultra means above, so we've got above violet. ultrasound above sound. Here we've got ultraviolet above violet. We get UV light. We take that UV light, we squash a little bit more, we're getting smaller and smaller. Now our wavelength is about the size of an atom. It's tiny, yeah? 10 to the minus 10 meters in wavelength. Very small, very, very small. So when we start to get things like X-rays, we take it and squash it even more, we get to gamma rays. So something we need to know is we need to know all the names of these electromagnetic waves. And we also need to know them in order. We need to know that radio's the longest. We need to know visible smack dam in the middle. And we need to know gamma rays on the other side. So remember, those radios are as long as buildings. And those gamma rays are as small as atomic nuclei. Yeah, in terms of that wavelength. Very, very dangerous, which we're going to talk about in a second. So I think it should be pretty easy to remember radio, gamma, or at either sides of the spectrum. And we know visible smack dam in the middle. Either side of visible, well, we've got above violet, we've got ultraviolet, and we've got below red, we've got infrared. Infra means below. So by remembering a couple of those facts there and kind of what they mean, it might be able to help us establish the entire order in our brains. But we are going to be doing other things to look at the order. Now, I want to just talk about a couple of the relationships that go on here. Now, something that we do know is wave speed equals frequency times wavelength. Okay? Now, if our wave speed is constant, and it's always the speed of light, 300 million meters per second, that means if we make the f really big, the wavelength must become really small, so that this equation still makes sense. Or if we make the wavelength really big, the frequency must become really small, so this equation still makes sense. So that's telling us that at this end, with the radio, right? At this end with the radio, it's got a long wavelength. It's got a really long wavelength, yeah? And it's also got a low frequency. While the gamma ray's got a really short wavelength and a really high frequency. When one gets big, the other gets small. When one gets small, the other gets big. Yeah? So this end over here, is high frequency. And this end over here is low frequency. Because think about it, if the gamma rays are like really close together like this, there's going to be loads passing per second. That's what frequency means. How many waves are passing per second? And if the radio waves are as big as buildings, then there's not going to be many passing per second. They're going to have a low frequency. Okay. So let's talk about these ones with a high frequency. When something's got like a really high frequency, a type of radiation, and these waves are a type of radiation. Radio is a type of radiation. It's a safe type of radiation. So don't be scared of that word, but it is something that radiates, right? Some types of radiation have enough energy to come from to remove electrons from atoms. Yeah, you have this energy with high frequency. Frequency is proportional to the energy. If you've got really high frequencies, you've got higher energy. You've got higher energy because it's really frequent, right? And the types of radiation that have this energy can remove electrons from atoms. So this electron here, it has a wave coming in, and the electron, it gets shooted off, it gets ejected, and it gets removed from there. This is known as something called ionization because it creates ions. It creates ions. Remember ions? I'm not sure, you're going to have to go look that up. Maybe look in your chemistry book. Ions are atoms which have an imbalance of charge. So they've either gained extra electrons to become negatively charged, or lost and ejected electrons like we have in this scenario to become positively charged. Now, ionizing things like your cells is a bad idea. ionizing things like your cells will damage them because you've pulled electrons. Electrons have been ejected from it. And this can lead to mutations on a big scale. Mutations of cells are known as cancers. So you start to get a cancerous tumor collection of cells because they've had their electrons ejected, they've become ionized, and everything starts behaving not as it should because that balance, that equilibrium's been lost in the biology. Now, something that's interesting here is in the same way that ionization can lead to cancer, ionization can also treat cancer. And it's the same principle. The ionization, the high energy from the high frequency disrupted the cell and made electrons eject, and it killed some parts there. If you used a lot of energy and a lot of frequency, you could just entirely ionize and entirely kill a cell. So that would be useful to kill the cells that we want rid of. Yeah, that would be useful to kill those cancer cells. We just have to be really sure that we're killing the cells we want to kill, and we're not just ionizing more of the body and causing more problems. Let's move on. So here we've got a list of our electromagnetic spectrum again, all in order, and we can use this to talk about the ionization we were going on about. So down at the bottom, we've got the radio waves, the really high wavelength, the long wavelength, and the gamma ray at the top, the really short wavelengths. The radio waves as big as buildings, the gamma ray is like as small as a atomic nuclei. So because this has got a really long wavelength and it's really long, it's going to have a low frequency, and this one's going to have a much higher frequency, more waves passing per second. Try not to associate the frequency with how quickly the wave's transferring, because we know they both have the same c. We know they're both traveling at the speed of light. So try and be careful with that. Frequency is just more how frequent it is before it starts again. Because it's got the high frequency, it's got the high energy. Because it's got the low frequency, it's got the low energy. Because it's got the high energy, it is highly ionizing. Which is why I've put these three in yellow, because they're the ionizing bits of radiation. The ones with short wavelengths are ionizing, and they have the possibility to do all that disruption we've done before, that we talked about in the previous slide. So the gamma, the X-rays, and the ultraviolet, they have the ability, they have the energy levels to disrupt cells and eject electrons and turn, regular cells, regular atoms into ions because they've ejected electrons from them. And so that's going to associate risks with them. An increasing level of risk, the more ionizing they get, because the more energy they have. So gamma is going to be our riskiest. Radio waves, pretty safe. Radio waves are all around us, yeah? So you've got giant waves the size of buildings going through your body, and it's not causing you any problem. They're transmitting through you, and it's fine, right? If that same thing was happening with those really small gamma rays in terms of their wavelengths, we'd be in a lot of trouble. It would be very, very different. And that's something we need to know. So we're going to talk about a little bit later, but in the meantime, you can go out and find for yourself. We need to know the uses, of which there is multiple for each of these. Radio waves, communication, broadcasting signals, right? We need to know the uses for each of these waves. We also need to know dangers, hazards, the risks. So radio waves, what are the uses? Well, communication, Wi-Fi signals, okay, transmitting signals, great. Well, the dangers of radio waves, well, none, they're safe. We have to do that for each of these electromagnetic waves. We need to know these electromagnetic waves in order. We need to know this one's got a really long wavelength, this one's kind of in the middle, this one's got a really short wavelength. We need to know these ones in yellow are ionizing. We need to know their uses, we need to know their dangers. And we'll talk about those a bit more together later, but right now I want you to find out. I want you to investigate these because there is loads and loads and loads of uses for these electromagnetic waves. These transverse waves, you know, traveling in straight lines at the speed of light. Yeah, there's loads and loads of uses for them. They're really, really important to our day-to-day life. So find some uses, find some dangers. You should be able to find a bunch of uses for each of them. I promise you that, because the application is all-encompassing, very, very widespreading.